Hello and welcome to our sections on light, starting with the properties of light. So, as said before, light is a combination of kind of the ideal of waves that we got from talking about sound and the ideal of electromagnetic radiation, which we talked about last chapter and in chapters previous to that. As a reminder, a change in an electric field causes a change in a magnetic field, which causes a change in an electric field. With this, if you have a magnetic field and an electric field next to each other, they will push each other forward in a direction of wave travel, similar to sound, but with transverse waves rather than longitudinal waves, and electromagnetic radiation, an electric field and a magnetic field, rather than just traveling through a medium. So, one of the things is that light doesn't need a medium to travel through. It is just an electric magnetic wave which is passing through a vacuum or through a material. And that means that instead of only being something that travels through a medium, electromagnetic radiation can travel through space as well. Because light is a wave, and it travels at a constant speed in vacuum, that means that there are different frequencies and different wavelengths associated with these frequencies. What we see as visible light is from about 420 to about 760 nanometers of wavelength, whereas what we see as infrared light has a lower frequency but a higher wavelength, and ultraviolet light has a higher frequency but a lower wavelength. Because light is a wave, it travels in a vacuum at a speed of 3 times 10 to the 8th meters per second. This is actually very, very close to the exact speed of light because the speed of light is one of those things that we use to define other constants. So we define the meter and the second by the fact that light travels at about 3.0001 or something like that times 10 to the 8th meters per second. However, when it goes through a material, the light is slowed by electromagnetic interactions with electrons dependent on the material and goes at a speed slower than the speed in a vacuum. So what you see on the left-hand side is a cartoon of this. The light interacts with electrons, which take a little bit to be excited and then kind of burp out the light to another electron, which gulps it up and then burps it out, and so on and so forth. So that as there are electromagnetic interactions and there are electrons and atoms in the material, they slow down the light. This also gives us an inkling that electromagnetic radiation interacts with the energy of particles, which is going to be something that is going to be very important when developing more modern physics ideals. When such materials as glass and water allow light to pass through in straight lines, we say they are transparent to light. To understand how light travels through a transparent material, visualize the electrons in the atoms as transparent materials as if they were connected to the nucleus by spring. When a light wave is incident upon them, the electrons are set into vibrations. Materials that are springy respond more to vibrations at some frequencies than at others. Bells ring at a particular frequency, tuning forks vibrate at a particular frequency, and so do the electrons of atoms and molecules. The natural vibrational frequencies of an electron depends on how strongly it is attached to the atom or molecule. Different atoms and molecules have different spring strengths. Electrons on the atoms of glass have a natural vibration frequency in the ultraviolet range. Therefore, when ultraviolet rays shine on glass, resonance occurs and the vibration of electrons builds up to large amplitudes, just as pushing someone on the resonant frequency of a spring builds to a large amplitude. The energy received by any glass atom is either remitted or passed on to neighboring atoms by collision. Resonating atoms in the glass can hold on to the energy of the ultraviolet light for quite some time, about 100 millionths of a second. During this time, the atom makes more than 1 million vibrations and it collides with neighboring atoms and gives up its energy as heat. Thus, glass is not transparent to ultraviolet light. At lower wave frequencies, such as those of visible light, electrons in the glass atoms are forced into vibrations but at lower amplitudes. The atoms hold the energy for a shorter time with less chance of collision with neighboring atoms and with less energy transformed into heat. The energy of vibrating electrons is re-emitted as light. Glass is transparent to all frequencies of visible light. The frequency of the re-emitted light that has passed from atom to atom is identical to the frequency of the light that has produced the vibration in the first place. However, there is a slight time delay between absorption and re-emission, and is this time delay that results in a lower average speed of light through a transparent material. Metals, by contrast, are opaque. Because the outer electrons of atoms in metals are not bound to any particular atom, they are free to wander with very little restraint through their materials, which is why metal conducts electricity and heat so well. When light shines on metal and sets these free electrons into vibration, their energy does not spring from atom to atom in the material, but is instead reflected. That's why metals are shiny. Light also casts a shadow, which is the absence of light. So if light is blocked by something that is opaque, then instead of seeing light, we will see a shadow. There's also something in addition called the shadow, which is called the penumbra, which is caused when some light is able to get through, but not all of the light is able to get through, and that's going to be kind of hazy shadow that you see. So, looking at lunar phases, you see a full moon when all of the light from the sun that would pass over the Earth is going to not interact with this moon at all. So all of the light from the sun that passes over the Earth casts a shadow behind it, but that doesn't cast a shadow on the moon, and that causes a full moon. A lunar eclipse is when the moon is completely in the Earth's shadow, and then a new moon is when observers on the nighttime side of Earth are out of view of the Earth's shadow, and observers in the shadow of the moon witness a solar eclipse when the moon is in between the Earth and the sun and completely casting out the shadow. But as you'll see on the bottom diagram, not all of the shadow is cast all over the Earth. So in many places in the Earth, you're only going to get a partial solar eclipse, which is when you see the penumbra, but not the total solar eclipse, which is going to be when you just see the dark shadow of the moon as the totality of the Earth is covered by, or the totality of the moon is, the sun's light is covered by the moon. Finally, I want to talk about the eye, which is a very specialized mechanism for seeing light and interpreting the different colors and the different intensities of light. So the cornea lets in light, which is passed through the iris, which is the colored part of your eye, which can go big or small and determines the size of your pupil. So the pupil is just a hole into your eye where the iris controls how big the pupil is and how much light is able to get through. This light is then focused with the lens into the retina and the fovea. There is a blind spot where the lens can focus light, but it's going directly to the brain, so it doesn't have any of the rods and cones, which are in the retina and the fovea, in order to understand what is going through the material. So the rods and cones are the two nerve endings or the two receptors which interpret and receive light. So rods basically just get a black and white image, and cones get a color image, where cones are going to be mostly focused in the fovea. They're mostly going to be in the fovea, while as rods are more evenly distributed throughout. And cones see red, green, and blue, as well as their inverse colors, or the lack of red, green, and blue, as the case may be, and use that to interpret the color of what you're looking at. So, one of the interesting things about this is that we're going to talk about colors more, but because the retina is mostly rods and only the fovea is really cones, only what you're really, really focused on, what's really in front of you, is going to appear like a colored picture or is going to have properly colored pictures. And this leads to a bunch of different uh, optical illusions, which are in the book and which uh, you can also see online, where we make assumptions based on what color we think should be there, but we don't necessarily see the color. We just process it and make the assumptions based on our experiences. And most of what we actually see is the color that is right in front of us. So our periphery vision, I believe, I don't think they go over this in the book, but unless somebody in eighth grade science was lying to me, our periphery vision is actually black and white and filled in by an optical illusion or by processing, which is actually done in the eye and mostly not in the brain. So we are going to get more into the ideal of color, which is what these cones understand, but color is just different wavelengths of light, and different wavelengths of light are interpreted different ways as different colors, and this is allowing us to see everything that we see around us as a different way instead of just seeing the like very basic ideals that you would see, the black and white that you would see if you were a dog or somebody with or some species with less uh complicated eyesight.